Hi, in this video we're going to be going over the Unit 10 problem set, and this will be the study guide for everything we learn in our kinetics unit. First, I'm going to go through this really quickly, and then we can start going. Alright, let's start. So first, doubling B will change the rate of formation of Y by a factor of what? Alright, so as we can see down there, it's asking us about the rate law. So let's just solve the rate law first, and it might help us doing the problems. Let's see how we can solve the rate law here. Let's choose experiment 1 and experiment 2. What information can we gather from these two? A and A will cancel, C and C will cancel, leaving you 0.2 divided by 0.3 is equal to the rate 10 divided by 15. And 2 over 3 is equal to 2 over 3. So now we know that B is to the first power. Okay, now let's use two different experiments. This time, let's see. We can do 3 and 4. This way, 0.2 and 0.2 will cancel out. 0.02 and 0.02 will cancel out, leaving you 0.08 and 0.016 for C. So when we use experiment 2 divided by experiment 3, we'll have 0.08 divided by 0.16 is equal to the corresponding rate, and it is 80 divided by 160. So what does this tell us? This tells us that C is also to the first power. 1/2 is equal to 1/2. 1/2 to n power to the x power is equal to 1/2, and that will be 1. So now all we need to do is find A. Now there are no 2 points where C and B cancel out with each other, leaving you only A to work with. So this time let's just take reaction 1. Rate is 10 is equal to, we need to do a ratio, sorry. Down there, let's do reaction 1 divided by reaction 2. No, we can't do that because A will cancel each other. Let's do reaction 1 and reaction 3. Experiment 3. So experiment 3 is going to be 80 is equal to A 0.1 to the nth power times B, which is 0.02 to the first power, times C, which is 0.04 to the first power, as we found over here already. Now in experiment 3, it will be 0.02 to the nth power times 0.02, 0.2, not 0.02 for A. 0.2 m times 0.02 times 0.08. To both of these are to the first power because we already found that B and C are to the first power. Now let's solve this. 10 divided by 80 gives us 0.125 equals 0.02, 0.02 and 0.02 can cancel each other. 1/2 m times 1/2. So if we divide 0.125 by 1/2, that will give us 0.25 is equal to 1/2 0.5 to the nth power. So 0.5 times 0.5 is equal to 0.25. Therefore, m is equal to 2. 1/2 squared is 0.25. Now we know A is second power. So let's go back to 4. What is the rate law? Rate law will be K times A to the second power, B to the first power, and C to the first power. Now we can come back to number 1. Doubling the B will change the rate of formation Y by a factor of 1. So B is to the B is the first order. So when you double something in first order, it's gonna double the rate formation. And our answer for that will be and so that's why our answer for that is D. Next, the rate of formation is Z in experiment 3 in molar per hour. So Z. Experiment 3, we're told that 80 is for Y. Now for every 2 moles of Y, there's 1 mole of Z. So you can do, where are we? 80 for Y, and for every 2 moles of Y, we have 1 mole of Z, which will give us 40. 80 divided by 2 is 40, which is how we get D again. The rate of disappearance for C in experiment 3. Okay, now we're looking at C, right? We're same for Y, and we're looking at 80 again. So 80 times 3 over 2 will give us what? 80 divided by, oops, sorry, it said experiment 2. Experiment 2 will have 15. 15 for y, for every 2 moles of y, we have 3 moles of C. So 15 divided by 2 times 3 gives us 22.5. Our answer is E. 4, we just found it. 5 will should be the rate of formation of y for experiment 5. Rate of formation for 5, okay. This one, let's use the rate law. Rate is equal to K, which we don't know yet. We can do that number 6 first. What is the value for the specific constant K? So in order to do number 5, we have to know K, but we have to find K first, which is the number 6. So let's do number 6 first. Let's do 10 molar per hour is equal to 0.1 squared times 0.02 times 0.04. I'm just using experiment 1 times K. So if you use 10 divided by 0.1 squared, divided by that by 0.02, divided that by 0.04, that'll give us 125.0000. So if we do 1.25, it's 1, 2, 3, 4, 5, 6. So 1.25 times 10 to the negative 6 power. Now that we know that, we can come back to number 5 and use rate is equal to 1.25 times 10 to the 10 to the 6th power times a squared. A for experiment 5 will be 0.050, 0.05 squared times 0.01 times 0.08. So 1.25 e to the 6th power times 0.05 squared times 0.01 times 0.08 gives an answer of 2.5. And that is our answer of A. Number 7, after a long time, assuming any reverse reaction can be neglected, what will be the concentration of Z in experiment 3? Okay, let's take a look at experiment 3. We have, now we're looking for the concentration for Z. And this is when we need to use a Rebecca chart, RBCA. RBCA. The reactant is A plus 2B plus 3C makes Z plus 2Y. Before, let's say we're using experiment 3. Yeah, we're using experiment 3. So experiment 3 will be 0.02. No, sorry, 0.2. B will be 0.02. C will be 0.08. Now, which one is the limiting reactant? Let's take a look. First, we divide 0.2 by A, which is by the moles of A, which is 1, which is 0.2. Now, we have A, 0.2. B is 0.02 divided by 2, which is 0.1 because there's 2 moles, 0.01. And C will be 0.08 divided by 3 moles, which is 0.02667. Now, which one is the smallest? B. B is our limiting reactant. So, minus 2 divided by 2, 0.02, etc., etc., etc. Now, we're only looking for Z. So, Z will be started with 0 and plus 2 over 1. No, 1 over 2. Because for every 1 mole of Z, there's 2 mole of B. And it's going to be 0.02. Now, what is that? 0 plus 0.001, which is 0.002 divided by half, will give us 0.001 molar. So our final answer is C, 0.001 molar. And again, I just found the limiting reactant, which is B, and then used our RBCA chart to get 0.001. 0.01. 8. It says these are the possible hypothetical reactions. Now, when A and B are double, the initial rate of the reaction will increase by a factor of 8. Now, if you know your rate laws good enough, you'll easily be able to know that is D. But what if you don't and you want to find an easier way to help yourself out? What you can do is plug numbers in for A. So let's assume A is 2 and B is 3. Alright? 2 squared times 3 gives you 12. Now, when A and B are doubled, now the new A will become 4 and the B will become 6. 4 squared and times 6 gives you 96. 12 vs 96. Now, we double check. Is 96 divided by 12 8? 96 divided by 12 is 8. So, we know that when you use reaction D, when A and B are doubled, the initial rate of the reaction increased by a factor 8 as it went from 12 to 96. So, the answer is D. Now A and B are double, the reaction only increased by a factor 2. Now why would that happen? When you double both of them, only increase by a factor 2. That means one of them has to have, that means one of them is first order and one of them is zeroth order. We can see that's A. And we can double check our equation again. So let's set A as 2 and B as 3. When you plug this in, the normal will give you 2. Let's see what happens when you double both of them. A will be 4, B will be 6, but there is no B at all. So it's still A, K of A, which this time is 4. So it went from 2 to 4. Did it increase by a factor of 2? Yes, it did. So that's how we know our answer is A. When A and B are double, the initial rate does not change. That means it has nothing. It only has K, because there is no A and B. So no matter how many times you increase it by, the K of will not change at all. So our answers are D, A, and F. Which of the following is true for the rates of disappearance and rate of appearance? So NO appears twice as fast. So this is molar ratio, stoichiometry. 2 NOCl for 2 NO for 1 Cl2. So NO appears twice the rate as NOCl disappear. NO and NOCl are equal number of moles, so they disappear and appear at the same rate. A is wrong. B, NO appears at the same rate as NOCl disappears. Yes, that is correct. As you can see, they're both the same number of moles. So that our answer is B. Now let's quickly check C, D, and D. NO appears at half the rate. Nope, their moles are the same. Cl appears at the same rate as NOCl. Nope, it's 1 to 2 ratio. Cl appears twice as fast as NOCl disappears. Nope, and NOCl appears twice as fast as Cl because NOCl is the one with 2 moles. So our answer is B. Number 12. Reactant A went through a decomposition reaction. The concentration of A is measured, and what do we see here? So time is 0, 1, 2, 3 hours, and molar of A went from 0.4 to 2 to 1 to 0.05. So what is the pattern that we see here? We can see here that after every single hour, the concentration of A decreases by half. So what does this tell you? This is a radioactive decay, radio with a half-life. Now we learned that most half-lives are in the first order. So now we look for the rate that is the first order. This is wrong. This is wrong. And now K, we did not change our K at all. All we said is that this is the first order because it's half-life. So the K should stay normal because in rate law, K always stays a K. You never find 2K and 1/2 K. So C and D automatically wrong. That makes the only possible answer A. A is the only one with a normal K, and it has a first order reaction since this data is a half-life, is a decay of half-life. Number 13, which one shows the A minus A to B? So A is a reactant and B is a product. That means A is being used from a big number to a small number, and B is produced from 0 to a big number. So which of these graphs shows A being used up and B being produced? Graph 1. As you can see here, A goes from here and gets used up until here. B starts from 0 and gets produced until here. And now after this, it's equilibrium. So this is the equilibrium point. Number 14, the following mechanism can be proposed for the reaction NO with this and this. Show the elementary steps of the proposed mechanism to provide a balanced. So our job is to write a balanced equation. Okay, so we have NO plus NO plus N2O2 plus H2 makes N2O2 plus N2O plus H2O. Now first we need to check if there is any intermediate or catalyst. N2O2 is produced, and then in the next step it's immediately used up, and then you do not find anywhere in the products or the reactants. So this is an intermediate. N2O2 is intermediate. They will cross out each other. Now let's see, is there anything that was used in the beginning and then also produced in the end? There is nothing. So there is no catalysts. Now that we know there are no catalysts, we can write this as 2NO plus H2 makes N2O plus H2O. And it's best if we include our state of matter. So NO is gas, H is also gas, N2O gas, and H2O is also in gas form. Write the rate law for each elementary step. Okay, elementary step 1, elementary step 2. We have rate is equal to K, just the two reactants, NO, square it because there are two NOs. That's for the first elementary step. Second elementary step would be rate equals K times the reactance, which is N2O2, times H2. And we're done. Identify the intermediates. We just did. It's N2O2. And identify catalyst. No catalyst. And our only intermediate is N2O2. The observed rate law is rate equals this times this. The proposed mechanism is correct. Now what can we conclude about the relative speeds of the things? Now the rate law for the overall is the rate law for the slow step. Now we see an H2 and we see NO2. So NO squared is what forms our N2O2. And our H2 can be found in the second step. So can our N2O2. Now what does this tell us? This tells us the second step is slower, because it is a rate determining step from our rate law over here. And number 15, the decomposition of hydrogen peroxide catalyst by an iodide ion. Okay, assuming the first step is the rate determining step, as you can see it says slow. Predict the rate law for the overall process. Now, rate law for the overall process is the rate law for the slow step. Now, do not get it confused by the overall reaction is a slow step reaction. Don't get it confused. So, the rate law for the overall process is the rate law for the slow step. So, it will be rate equals K times the concentration of H2O2 times the concentration of I minus, the two reactants. Right, the chemical equation for overall process. All right, now this time it didn't ask for rate law. So this time we actually have to add up all the reactant and products and watch out for the intermediate and catalyst. So plus IO minus plus H2O2 makes H2O plus IO minus plus H2O plus O2 plus I minus. Alright, let's see. I minus is here, react in the beginning, and it is produced again in the end. So I minus is catalyst. IO minus, on the other hand, is produced and then used up again and never appeared again in our reactants or products in the overall process. So IO minus is the intermediate. They'll cross out. And I minus is the catalyst. So we'll save this for later. So what is our final equation? Our final equation is H2, final overall process, H2O2 plus, no, 2H2O2, not plus anymore, makes 2H2O plus O2 plus I minus. Nope, not the I minus, because remember, the I minus will go on the top. I minus, since it is a catalyst. Now here it says I minus. Next, identify the intermediates and the catalyst. Alright, intermediate is IO minus, and catalyst is I minus, and I just explained why they are, and there we go. Number 16, below to answer the question about catalyst, is NO2 homogeneous or heterogeneous? NO2 is our catalyst. In the beginning it's gas, in the end it's also gas. So, NO2 is homogeneous. Is a homogeneous catalyst in this reaction because it has the same state of matter. Okay, finally, for the second order decomposition of hydrogen iodide at 700 K, the constant is this. So what is that? Alright, so it told us the second order. Now what is the formula for second order? A at time minus 1 over A initial is equal to K times T. Now we were told that K is this much, so K is 1.2 times 10 to negative third molar negative first times second negative first, and HI0 is 0.056. 0.56. Now we're looking for X over here, which is A of time. Now how long is the time? 2 hours. But be aware, it gave us molars to negative first times second to the negative first. So our time will have to be consistent with our unit for K. So since our time is in 2 hours, we need to convert it into seconds. 2 hours, 1 hour, 60 minutes, 1 minute, 60 seconds. So 2 times 60 times 60, which gives you 7200. Again, we have to convert this to seconds because our rate constant is in molar to negative first power times second to negative first power. Now we can solve. 1.2 e to negative 3 times 7200 plus 1 divided by 0.52 equals 10.45. Now we do 1 over 10.4257 gives us 0.0959. That is our concentration of HI after 2 hours. So now we're asked to find the optimum wavelength, and the optimum wavelength is basically where the wavelength is the highest, and that is approximately this point. So how long is this? This is around 720 mm at 1.0 joules. Okay, next, the student measures the absorbance of 0.08 m, 0. This, and multiple solutions. The data are plotted below. So the absorbance of the unknown concentration is 0.75. What is the concentration of the solution? Absorbance is 0.75. So about here, what is the concentration? About 0.28 molar. Beer's law includes three factors, and it is big A equals little a times B times C. C is concentration, B is length of the cuvette, and A is the molar absorptivity coefficient. A student handles the cuvette and leaves fingerprint on the path of the light beam. How will this affect our calculation? So this will be, it will increase the concentration because the fingerprint will absorb light. Now, why is this method of determining concentration of NaSO4 solution inappropriate, whereas using the same method for measuring NaCl would not be appropriate? And that is because NaCl is a different color, and so the absorption would also be different. Next, calculate the rate constant K. First, I calculate the initial rate of reaction. Rate is equal to negative changing concentration of A over changing time, which is, let's say, negative 0.289 minus 0.4 over 20. Negative 0.289 minus 0.4 over 20 minutes. That gives me 0.00555. That's the initial rate. Now we can find K, as rate is equal to K times the concentration of N2O5. That's our rate law. 0.00555 is equal to K times 0.4. So 0.00555 divided by 0.4 will give us K. And remember, this K is the concentration of A initial. So this will give us K at 0.013875. Now after what time will K? So this told us it was the first order. So ln of concentration of A at a certain time minus ln concentration of A initial is equal to negative K times T. Now after how long will ln 0.350 be minus ln of initial, which is 0.4, equals negative 0.013875 K, we found over here, times our time. So ln 0.350 minus ln of 0.4 divided by negative 0.013875 gives us 9.62 minutes. Okay, we should include units, and since this is the first order, it will be minutes to the negative first power. What will the concentration be after 100 minutes? Alright, so ln of x, which we're looking for, minus ln of initial, which is 400, equals negative 0.013875 times 100. Negative 0.013875 times 100 plus natural log of 400, 0.4, sorry, 0.4 equals that. Natural log of that gives you negative 2.30379. Now we'll have ln of x is equal to negative 2.3037900732. And this is basically base of e to the negative this number's power will be equal to x. So let's plug into our calculator and we'll get x as 0.0999 molar. What is the half-life of the reaction? Alright, the half-life will be T1/2 is equal to 0.693 over K. 0.693 over K, which is 0.013875, which will be 49.9 minutes, since our K is in minutes. Alright, now finally we're on the last page. Write the rate law. Alright, as you can see here, 0.2, 0.2, 0.2, 0.4. So if you use experiment 2 divided by experiment 3, A will cancel out, leaving us 1/2 equals to the nth power equals 3 divided by 6 is also 1/2. So B is to the first power. Now let's put M. So this time we're going to have to choose something different, like experiment 1 over experiment 2. 1.5 times 10 to the negative 3 divided by 3 times 10 to the negative 3 is equal to 0.1 to the nth power times 0.1, as we found B is to the first power already, divided by 0.2 to the nth power times 0.2 to the first power, as we found B already. So 1/2 is equal to 1/2 to the nth power times 1/2. 1/2 divided by 1/2 is 1. So 1 is equal to 1/2 to the nth power. Anything to the zeroth power is 1, so M is equal to 0. So over here, rate law will be rate is equal to K times A to the zeroth power times B to the first power. Calculate the value for the rate constant K. Easy. Let's just use experiment 1. 1.5 times 10 to the negative 3 is equal to K times constant of B, because A is to the zeroth power, so it will not matter at all. So 1.5 e to negative 3 divided by concentration of B, which is 0.1, gives us K as 0.015. Now what will the units be? Let's see, this is the first order overall reaction, because we only have B and no A. First order overall reaction will mean that K will have a unit of time to negative first power. Time in this case is minutes. Minutes over here, so our unit will be minutes to the negative first power. If another experiment is attempted when A and B both 0.02 molar, what is the initial disappearance? A would not matter because A is to the zeroth power. So it's basically saying X is equal to K, which is 0.015 times 0.02. 0.015 times 0.02 gives us 3 times 10 to the negative 4, and we can rewrite this to 3 significant figures, 3.00 times 10 to the negative 4th power. Consider for experiment 2 and substance D for the following questions. Alright, substance D. Experiment 2, what is the concentration of A remaining when half of the original B is confused? So in experiment 2, right? Experiment 2, it asks for how much A remains after half of B is consumed. So we have 0.20 molar of B. Now after half of that is confused, we're going to have 0.1 molar of B left. So far makes sense. And then for every 2 moles of A, we have 1 mole of B. So 0.1 times 2 will give us 0.2 molar. So 0.2 molar of the 0.2 molar will be used. And how much will be remaining? We only have 0.2, and now all 0.2 is used, so none remain. If experiment 2 goes to completion, what is the final concentration of D? Alright, now we need to find which was the limiting reactant, just like number 7 we did up there. So limiting reactant will be A, obviously, right? Because both of these are 0.2 and A have 2 moles. So A goes to completion. Let's do an RBCA chart. We have 2A plus B. We only care about D, so let's just ignore C. So 2 will be minus 2 over 2 times 0.02. D is only starts with 0 plus 1 over 2. Every 1D there are 2A. So 1 over 2 times 0.02 as well. So it's 0.01 basically. So our answer is 0.01 molar of D. What is the final concentration of D? It will be 0.01 moles, because we just found using our RBCA chart for every 2 moles of A, this 1 mole of D. Number 21, the zero order decomposition of ammonia versus this, the rate is this. Alright, so rate is equal to K times concentration of NH3. It told us, oops, geez. Our NH3, it told us the concentration, so we can easily find rate. We can easily find the rate constant. So 3.40 times 10 to the negative 6 is equal to 0.0452 times x. So 3.4 e to negative 6 divided by 0.0452 will give you 7.522 times 10 to the negative 5. Now that is k. To find half-life, half-life is equal to 0.693 divided by k. So 0.693 divided by our previous answer will give us half-life of 9,212. Let's see, what's our k? K is in seconds. More like 13. It rounds up to 13, sorry. But yeah, it wants us in minutes. So we're going to have to divide this by 60. 9213 seconds divided by 60 to get minutes. Divide that by 60 again to get hours, which will give us 2.56 hours. Number 22, we have this graph. How many elementary steps? We have 1 and we have 2. 2 steps. Which step will most likely be the fast step? So first we have from transition state to our reactants. Second, we have our transition state to the intermediate. So which of these EA is bigger? Remember, bigger EA means slower. So obviously step 1 is slower. So which is faster? Second step is faster. Now how do you know where to draw the EAs? First we start with our reactants and go all the way to transition state. Then it dips down to the intermediate and then starts rising again. So our second EA will be from the intermediate to the second bump. And that will be the second EA for when you're looking at multi-step equation energy profiles. Now, is step 1 endothermic or exothermic? It goes from low to high, right? The intermediate position is higher than that of the reactant. So this one will be endo. Products have more energy than the reactants. But the overall endo or exo, products, no. Reactants line is over here, products line is over here. Products line is lower than the reactants line. So overall, this is exothermic because the products have less energy than the reactants. Now the diagram ball, finally we need to draw a proposed change to the energy pathway if the catalyst was added. Alright, catalyst added. All we need to do is minus our EAs. So we can draw, but remember, the energy at reacting and product doesn't change. So we can start our line from here, and we can basically draw however we want. I think this will look good enough. And this will be our catalyst. This will be our line, how our line will look in the addition of a catalyst. And that is it for our kinetics unit study guide. Thank you for watching.